All right, guys, welcome to Let's Get to the Marks. We're looking at an NMR question. So, question five, this question's about compound Z with a molecular formula C7H12O3. Figure 7 shows the infrared spectrum of Z. Okay, we've got transmittance on the left here, and we have wave number at the bottom. Identify the bond that causes the absorption at 1725. Once again, always pause the video, have a go before looking up and watching the walkthrough. All right, there we go. So that's the wave they're talking about. This one at 1725. All we have to do here is flip to our data sheet over here, and we need to make sure we're looking at the right one. And it was asking us about infrared. So we check this out and we go 1725. You can see there 1725 falls between these two numbers, these wave numbers. And so the bond we're looking at is the carbonyl bond. Awesome. So let's zing back there and put our answer in. So the answer here, we're looking at the carbonyl bond. And hopefully that's a nice, easy starter for this question. All right, let's zing down to the next part of the question. So, figure 8 shows the C13 NMR spectrum of Z. Here's figure 8. You can see all these lines here. We've got chemical shift in ppm along the bottom. How many different carbon environments are there in a molecule of Z? So once again, pause, have a go, and I'll explain. Okay, so the way to do this, the number of different carbon environments shown by the C13 NMR is the number of peaks. So count the number of peaks. We got one, we got two, we got three, we got four. Now here's a tricky bit. You got five, you got six, and you got seven. Now this might give people some confusion. Okay, the answer is actually seven, as you can see there, and that might seem obvious, but a lot of people might get this mixed up with their proton NMR or H1 NMR. Now, in C13 NMR, you don't get splitting patterns. So you don't want to start thinking, oh, that's a doublet or whatever. That's not a splitting pattern. They're just two peaks very close together in the chemical shift. Okay, so it's seven peaks. All you really get from C13 NMR, all you can really work out is the number of different carbon environments, which is shown by the number of peaks. And then you can also use the chemical shift to give you an idea of the groups. Let's move on to 5.3. So I'm going to zing down a little bit here. And we can see here for 5.3, it says state the type of carbon environment that causes the peak at 174 ppm. So we're going to go along here and find 174. It's got to be this one here, right? It's the only one in that region. And we need to use table C in the data booklet to answer the question. So we need to swing over to the data booklet, and table C is here. And we need to go down the C13 NMR chemical shift data and find 174. And you can see here, it looks like it's going to be an ester. So zinging back here, it's going to be an ester. So the type of carbon environment that shows this is an ester. So you're really looking at, yeah, something like that. You've got that environment. All right, let's zing on and stop the waffle. So let's go to 5.4 in this question. Table 2 shows the data from the H1 NMR spectrum for compound Z. So this question is testing you on your infrared, just for a mark, a couple of marks on CNMR, and then we're moving on to proton or H1 or 1H NMR. So we've been given chemical shift data here, which can help us identify the group responsible, integration ratio, which I'll talk about in a second, and the splitting pattern. So we get that extra splitting pattern and integration ratio that we don't normally get with CNMR. Explain what can be deduced from the splitting patterns and the chemical shift values for the peaks at 410 and at 126. So we're looking for our peaks at 410 and 126 and what can be deduced from that. It then says deduce the part of the structure Z that causes these peaks 410 and 126. So that's going to be the fifth mark. 2 marks for explaining 410 and 126, and then one extra mark for putting them together to make the structure that causes those two peaks. It says use table B in the data booklet to help you answer this question. So let's tackle it, right? So Straight off, I'm going to look at 410 first. It's the first one that hits the eye. So chemical shift at 410. Let's go check out what that could possibly be. So we're going to come down here. This is table B. Let's go down to 410. We can see 3.7 to 4.1 or 3.1 to 4.2. So these are my two possibilities for the chemical shift at 410. It could either be this hydrogen atom, which has got a halo attached or a halogen attached, or it could be this hydrogen atom, which has an ester link. Now, bearing in mind that we just identified there was an ester link, we're probably going to be the ester link. And bearing in mind that we also know from the stem of the question right at the very start, they told us the formula was C7, what was it, H12, and it was O3. That was the formula they gave us right in 5.1 at the start. So there's no chlorine atom or bromine atom. There's no halogen there. So we definitely know that the group or environment responsible for the 410 chemical shift is this one here. All right, let's go back, put that on our answer, and then we'll check the rest of it out. Okay, so we want to say there's a ester link at, whoopsie, 410 from chemical shift. What I can also tell from the data here at 410, the integration ratio is 2. So I'm expecting integration ratio is 2. So 2 hydrogens in this environment. It's not always 2. Sometimes it's a ratio, but in this situation, as it normally does, it's telling us there's 2 hydrogens in this environment. So we know there's the ester link from 410. We know the integration ratio tells us there are 2 hydrogens in this environment. Now we've got a splitting pattern, which is a quartet. So the splitting pattern, I can't fit it all in. So quartet tells us adjacent carbon has 3 H's attached. So straight away, what we're looking at is it's telling us that the neighboring carbon next to the hydrogen of this one has got 3 hydrogens attached. So what I'm kind of thinking here, folks, is we got this ester link, okay, like so, and then we've got CH2. Why do I know it's CH2? That's because the integration ratio was 2. So this hydrogen here, it could be the one below, the one underneath, it could be either hydrogen, is giving me the 410 chemical shift because it's saying it's attached to an ester link. And also that we have a quartet here, and that is telling me that it's adjacent to a carbon, the carbon attached to this hydrogen is adjacent to a carbon with 3 hydrogens attached. Quartet is 9 times out of 10 telling you there's a methyl group attached. So really, that is what 410 is telling us. Okay, back from the mini break. Let's go. Where were we? So what we're saying here is that this hydrogen, the fact that this hydrogen has an integration trace of 2 tells me there's 2 hydrogens. The fact that it has a quartet tells me that the adjacent carbon atom, to the carbon that this hydrogen's attached to has 3 hydrogens. Now, normally a quartet is normally a CH3 group. Now let's look at the 126. So if we look at the 126, and we can just pick any of these hydrogens, any of the 3, and say it's 126, we can see, why am I assuming this is the 126? Well, it has an I trace, integration trace of 3, telling me that there's 3 hydrogens, and it also says that it produces a splitting pattern, okay? That is a triplet. Now, what does the triplet tell you? With splitting patterns, they call it the N+1 rule. I like to think of it as the N-1 rule. So you take the triplet, and if you take away 1 from that, you get 2, and that tells you the amount of hydrogens next door. But most of the books call it the N+1 rule, and they say the splitting pattern is 1 more than the number of hydrogens on the adjacent carbon. So if you get a triplet, it tells you there's a CH2 next door. Okay. or there's two hydrogens attached to the carbon next door. So all of that information is there. So we're going to put that down here, and we're going to say from this, we're going to say that we have the integration value or trace or ratio is 3. So 3 H's in this environment. We also want to say, I can't fit all this junk in. Splitting pattern triplet um, tells us adjacent or neighboring, if you prefer that word, um, carbon environment has 2 H's. So it makes perfectly sense that we have an ethyl group here, a CH3 and a CH2. And judging from the shift at 410, we could tell that it was an ester link. So for the final part, it says what bit of the structure is responsible for this. And essentially, we've got that going on. So we've got this is structure, that is the part of structure Z that gives us the 410 and the 1.26. So that will get you 5 marks. You're going to get 2 marks for the information. So even if you find it really impossible to do what I've done here and put the structure together, and you find that really, really hard, you can still get 4 out of 5 marks just by interpreting the integration trace and the splitting pattern. Just by saying, oh, well, look, it's got a 2 on the integration ratio. That tells me there is 2 hydrogen atoms in the environment, and the splitting pattern's a quartet. It tells me that the environment next door, the carbon atom next to the carbon with these 2 hydrogens on, has 3 hydrogens attached because it's a quartet. So, excuse me, just explaining the integration ratio and splitting pattern will get you most of the marks, even if you can't do this bit. Excuse me. So now what we're going to do, we're going to move on and we're going to flick down. 5.5, deduce the part of the structure of Z that causes the peak at 219. Well, let's check out 219. We've got to deduce the structure that causes the peak at 219. So if we look at 219 and we go to our chemical shift, let's check that out, check that out, check that out. So 219, we're going to find that, bada bada bing, bada bong, right here, look, 2.1 to 2.6. I'm on the H1NMR. We're going to find, again, I've got a carbonyl group, and this is the hydrogen that is telling me there's a carbonyl group there. So that's the hydrogen responsible for this pattern. And we're looking at a carbonyl attached. So let's zing back and put this piece together. So what were we doing? We were looking at 219. It's telling us that we have this hydrogen here, which is giving us a 219 parts per million or whatever that ppm chemical shift is. And it was telling us that there is a carbonyl group attached. So that is the structure responsible. However, we've also got some other information. We have an integration trace or ratio. I keep calling it trace. It's not a trace. That's a line on a graph. Sorry about that. Keep referring it to that as blah, blah, integration trace. This is an integration value or ratio, and of 3 tells us 3 H's, okay, in this environment. Now, what some of you may get confused with is you might go, oh, but doesn't the integration trace tell you about the amount of hydrogens next door? No, it tells you about the amount of hydrogens on the immediate carbon atom. So it's telling me that there are 3 hydrogens directly attached to this carbon atom here. And actually, it's the splitting pattern, the singlet, that tells me about the next door. So singlet gives you the information about, so the singlet is telling me about the carbon next door. This is the next door neighboring carbon. And what a singlet tells you is there are no hydrogens attached. So that makes sense, right? There's no hydrogens attached on this on this carbonyl group. So it does perfectly all fit together. And that is the part of the structure for 5.5. So that is your answer for 5.5. Boom. All right, we're going to move on, and I'm sure they're going to ask us to piece the whole thing together, which is always a bit difficult to do when you're on the old computer screen, but we shall give it a good go. Right, figure 9 shows the H1 NMR spectrum of compound Z. Okay, so we've got some splitting patterns. We've got the chemical shift. Suggests why it would be difficult to determine the structure of Z using the spectrum in figure 9 without the information in table 2 on page 13. So they're saying if we just had this, could we work out the structure? It would be difficult without table 2. What have we got that's extra in table 2? We've got this, the integration ratio. That graph only gives us the chemical shift and the splitting pattern. It doesn't give us the integration ratio or value or ratio, whatever. So what we want to say here is um, this does not have integration ratio. So it's going to be hard because this doesn't tell us the integration ratio. So it's going to make it a little bit more difficult. And that'll get you a mark for that. Now we're going to be on to, I presume, the final part of the question. Deduce the structure of Z. So now what we got to do is we've got to put it all together based on the information we were looking at. So let's do that. And it's only one mark. So like I always say with HNMR, if you learn how to interpret splitting patterns and integration trace and use the chemical shift table, you can get most of the marks without being able to do the hardest bit, which is put the structure together. But let's give it a go. So let's remember right at the start, the first thing we did at the start of this question was we looked at 410. We looked at the hydrogen that gave us a chemical shift of 410. And remember, it had an integration trace of 2. So that told us there were 2 hydrogens. And it told us that it had a quartet splitting pattern. The one at 410 had a quartet splitting pattern. So it told us that the carbon next door had 3 hydrogens attached. Beautiful. And then we know that this was 1.26. And this told us, confirmed our stuff. It basically gave us a triplet splitting pattern, which means the carbon next door's got 2. The 126 had an integration trace of 3, telling us there's 3 hydrogens. So it's absolutely beautiful. We got all of that correct. Now, when we looked at the 410 ppm, this thing here, it also told us that we were looking at an ester linkage. It told us we were looking at an ester linkage. And so if we got an ester link, we know that's the next part of the situation. Now, for 5.5, I'm not going to zing back on the paper because it's caused me issues. For 5.5, we were looking at the hydrogen in the table that gave us a 2.19. If you look up on your chemical table now, the 2.19 also told us that it was attached to a carbonyl. So this said, oh, I'm attached to a carbonyl bond. So there we go. That's what we got from the 2.19. It had an integration trace of 3, telling us there were 3 hydrogens. So we're dealing with a methyl group. And the 2.19 told us it's attached to a carbonyl. And it had a singlet splitting pattern. The singlet means there's no hydrogens next door. Now, I might say, oh, is that R there, all of this? And is this carbonyl this? But that wouldn't make sense because the formula we were dealing with here was H7, H12, O3, and they gave us that at the start of the question. And so if I put a CH3 on the end here, that is not really going to work. I'm not going to have enough carbons and I'm missing an oxygen. So what I'm going to do, this is likely to be the opposite end of the molecule. Let's have a little look. So just to show you this here, this is going to be the opposite end of the molecule. So this is what gave us the 2.19 shift. Remember, anything around the 2.19 is telling us it's attached to a carbonyl. And so that's the opposite end of the molecule. Now we have to look at the remaining 2 shifts. We've got a 2.56 and we've got a 2.60. And let's very quickly zing back up to the table. So you can see here, I've got 2.60 and 2.56. Both have got triplets. Both have got integration ratios of 2, and their ppm is basically identical. And so we'll look at what their ppm is. Just remember they've got an I integration value or ratio of 2 and they're triplets. Let's come back down, get a little bit of space going on. Okay, so what we're going to look at here, I've obviously got another carbon, and let's just say this is the 2.56. Let's see what 2.56 is telling us. We're going to go to the table. 2.56, look here, I've highlighted that in blue. The 2.56 and 2.60 are both attached to carbonyls. So let's go back. So what that's going to tell me, so look, it is attached to a carbonyl. Look what's next door. Remember, it had an integration value of 2. So that tells me there are 2 hydrogens attached. And it had, the 2.56 had a splitting pattern. Oh my days. It had a splitting pattern that was a triplet. What does a triplet tell you? Remember the n+1 rule? Tells me that it's next door to a carbon that also has 2 hydrogens attached, right? So that splitting pattern tells us about this neighboring carbon. And that all makes sense. Now, if I say this is the 260 hydrogen, again, it says it's connected to a carbonyl. That makes sense. Look, there's a carbonyl group there. So that makes perfect sense. And it had an I2, an integration value or ratio of 2, 2 hydrogens in its environment. And it also gave a triplet splitting pattern. It gave us a triplet split. And what does the triplet split say? Hey, it says the carbon next door has 2 hydrogens. And of course it does. Both are giving triplets because they're next door to each other and each of them has 2 hydrogens. So that is our final structure. Now, as I say, that's not easy to do, but you're going to score all the marks by interpreting the integration value or ratio and the splitting patterns and explaining what they tell you. That's how you can get all the marks. All right, people, remember sharing's caring. Help out our little poor science teacher. Hit the like, punch the bell, subscribe. Let's get to the marks.
You're still here? It's over.